All right, let's talk really briefly about real stellar spectra, because this is how we get most of our information about stars, and it's going to be the first chain in the reasoning of how we know so much, how we can calculate stellar parameters and things. Okay, so if we take the light from a star and we break it up into a spectrum, which is easy to do, right, through those little diffraction gratings or a prism or something, we see something like what we have on the left. Here, and there's a diagram just like this in the book, each strip running from violet to red is a spectrum of a star. You just take the starlight and you just break it up and you get a rainbow. But what Fraunhofer noticed in the 1800s, and we see it clearly now, is that you see these dark absorption bands. So what we see from stars is an absorption spectra. The outer layers of the star absorb some of the light that comes from the star. So we can look down here for common lines. Stars are, let me start off because I might forget about this later. I'm going to tell you in advance, it turns out that all stars have about the same amount of hydrogen in them. All stars are about 92-91% hydrogen. So that's something to keep in mind. Because when we look at the spectra of stars, some stars show these hydrogen absorption lines and some don't. And the key thing to take away from that is just because an absorption line doesn't show up, like down here, look at this guy. Look at the K stars and the M stars, and up here the O stars. It's hard to see that hydrogen alpha line, that red hydrogen line. It's hard to see it. And it's kind of not even there. So should we take away from that there's no hydrogen in this star? The answer is no. If we see a hydrogen line, that does mean that there's hydrogen there, no doubt about it. But if the line's not there, we can't say that it's not present. Only the conditions aren't right for it to be absorbed. Okay, so here's what's happening. Let's see if we can understand why some stars, like here, these stars right in the middle, the A-type stars, have really strong hydrogen lines. No doubt about it. You see it right there. Over here in the H-beta, the greenish line, you can see really strong hydrogen lines there. So what's happening is, suppose this is our standard little hydrogen atom. And suppose we have light from the star is coming in. Suppose it's, just basically white light, starlight. And what this means is that there's all sorts of light coming in. There's all sorts of light coming in. So there's violet, right? And there's blue. And there's green. All the colors of the rainbow. Yellow. Red. Right. All of these colors are coming in. The continuous spectrum is coming from the star. Now, when it hits a hydrogen atom, here's what happens. If an electron is sitting down here at level 1, well, nothing happens. All of that visible light just passes right through. It's a transparent gas. Hydrogen is transparent if the electron is just sitting down at level 1. Because it's not going to absorb. What does it have to do? In order to jump up to a different energy level, in order to jump up to level 2, it's got to absorb this much energy, and that's an ultraviolet photon, not a visible. So visible light, if it can't be absorbed, visible light just goes right through. Okay, so let's get rid of that. Okay, let's look at that. In the rainbow that's coming from the star, in all the colors that are coming from the star, in particular, there is this particular color. Remember 656, the H-alpha spectral line. 656 is a particular color, 656 nanometers. And that's included in that rainbow, right? So what happens if an electron just happens to be at level 2 and this red light comes and hits it, well, we know what happens. This is what we talked about last time. It will kick up to level 3. It will absorb that particular light, kick up to level 3. It'll hang out there for a little while and then fall back to level 2. And when it does that, it'll re-emit that flash of light, but in a totally different direction, so we don't see it. Right? If this was us back here looking at the star, everything comes to us but that particular color. Everything else goes right through. Everything else is transparent. But that one particular color representing the shift from 2 to 3 gets scattered out, gets absorbed and re-radiated in a different direction. We don't see it, and then we get these dark bands because it's been filtered out. Right? Same thing is true if the electron starts off at 2 and that special blue-green light, 486, if that hits it, that can kick it up to level 4, and then it goes back down again, re-radiates in a different direction, and so we get these. We get the blank spots corresponding to the 2 to 4 absorption. Okay, so in that way we have the absorption for all of these hydrogen lines. Okay, so we understand that. But notice what has to happen is that the electron has to be in level 2 for any hydrogen absorption to take place. How does it get to level 2 to begin with? Well, it gets kicked up there. Maybe 2 hydrogen atoms collide together. So in a cool star, if a star is too cool, then the interactions, the bumps between hydrogen atoms aren't energetic enough to kick the electrons up to level 2. The gas has to be a certain temperature in order for those collisions to kick the electrons up high enough. So in cool stars, it turns out you don't get hydrogen absorption lines because the cool stars E in level 1. The electrons hang out in level 1. The collisions aren't violent enough to kick them up. So they can't absorb hydrogen. You have to be in level 2 to absorb those visible hydrogen lines. So cool stars, even though there's hydrogen there, we're not going to see the absorption lines. Hydrogen's transparent. What about really hot stars? In really hot stars, what happens is that the collisions are so violent that the electrons are not kicked up to level 2, they're kicked up to level 3 and above, and even ionized right out of the atom. So again, they can't absorb the visible light. You have to be in level 2. So for really hot stars, the electrons are ionized, kicked up to level 3, and then ionized, kicked right out of the atom. So you're not going to absorb those particular colors. So it has to be just right, sort of like a Goldilocks problem. What is just right? Boy, that's sloppy. Just right, the temperature has to be about 10,000, it turns out, about 10,000 Kelvin. At about 10,000 degrees, the collisions are violent enough to kick the electrons up to level 2, but no higher. Most of them just sit at level 2. They can absorb the light, and then we get nice, strong features like that. So what I'm telling you is, if we see nice, strong hydrogen lines, that kind of tells us what the temperature of the star is. Now, in the old days, before we knew about electrons and energy levels, what they did was the stars with the strongest hydrogen lines, they just called type A. Type A had strong hydrogen lines. They didn't know why. They just cataloged them as type A. And then type B is a little bit less. Blah, 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 blah. All the way down to type M and O. These had very weak hydrogen lines. But later, when we began to understand what was really happening, classifying stars based on hydrogen line strength didn't make as much sense anymore, and instead we wanted to classify them according to temperature, which is what we were really interested in. So here's a common problem in astronomy, is that the books were already written and people already had memorized all the stars above and what their types were, so it just stuck. So unfortunately, they get all jumbled up. So according to temperature, type O stars are what turn out to be the hottest at about 40,000. These are the surface temperatures, about 40,000 degrees. I can't remember them off the top of my head, so I'm just going to do about. There's a more precise table in the book. Type B is something like, what is it, 20,000? I don't know, something like that. You can look it up. O, B, A, F, G. Daggone it, I'm going to run out of room. I got to make it a little smaller. O, B, A, F, G, K, M. So this is like 40,000. B's are like 20,000. A's are like 10,000. F's are like 8. G's are like 6. This is like the sun. The sun is a type G. And then you have K's at like 4,000. M's at like 3,000. Okay. So this is the modern system for classifying stars. Unfortunately, all the letters got jumbled up. And notice this kind of tracks with what we saw up there, that it's the medium temperature stars, the A's, that have the strongest hydrogen lines because they have the electrons sitting there ready to go at level 2. With the letters all jumbled up, it's sort of important to remember these in order, because in the future, whenever we talk about O and B stars, right away that should trigger in your head, ah, right, those are the hot ones. Or if I say K's and M's, that should mean the cool ones. And so there's nothing else to do really but just memorize the sequence. And to memorize a sequence, a lot of times a little mnemonic helps. So if you want, you can make up any one you want. The old quaint one from back in the 1890s was like, oh, be a fine girl or guy, kiss me. So you can use that one if you want, but any way that you want to remember them in order, that's cool. Okay, so this is the modern way that we classify stars. 7 major types. I think the book has 3 more types, but that's okay. I don't care about them. The other thing that we need to talk about is digitizing the spectra. When we see the rainbow of colors, that's what we used to do in the old days. Nowadays, you just have a computer look at it. And what the computer does is it just measures the brightness of all those colors. And then it just plots the brightness. So if I have, look down, I need to choose a different color. Look down here. The emission line spectrum. It's a black background, so it's dark. And then at particular colors, you have bright streaks. So in a graph, that corresponds to this over here, where there's nothing, and then at particular lines, at particular colors, at these particular wavelengths, you have bright spikes going up, because those are the colors. So we're plotting brightness. Sometimes it's called intensity, but that's always brightness. And then here on the x-axis is color. And usually it runs from violet over here to red over on this side. So with those particular colors, you get a little spike up because that means there's a color there. Absorption lines kind of run the reverse, right? There's a bright background, and the background follows this black body curve that we saw before. And then at those particular colors, it's black, right? So at those particular colors, we get downward pointing spikes because it gets dim at those colors. So it's this that we'll be seeing most often when we look at stars, is we see this continuous background, and then we see these downward pointing spikes. Those are the absorption lines. So that's what we'll see as we go. Okay, for example, finally, let's look at actual stars. Boom, look at this. Type O and B. So what do we see? We see a continuum background. The overall shape of this thing. If we were to continue, notice it cuts off. Oh, here's something. You'll okay. If it says angstroms down here, an angstrom is 1/10 of a nanometer. All you have to do is just forget about these extra zeros. This is still violet, and over here 7,000 is like red. That's 700 nanometers. So if it says angstroms, 4,000 to 9,000 or something, just chop off that extra zero, and then you got nanometers. Okay. If we were to continue this into the ultraviolet, what you would see is this overall shape would sort of peak up here somewhere and then come down. In the visible part of the spectrum, though, we don't see the peak. We only see the rise up to the peak. And so this is clearly a hot star, right? Because over here, maybe the peak is way over here at like 200 nanometers or something like that. So maybe this is a really, really hot star. So we don't even see the peak. And also, look, this thing tries to type the spectral lines for us. There's H alpha and H beta that I've circled, and look, you can barely even see it. There's virtually no lines there and no downward pointing spikes. So that means that the hydrogen lines are weak. Again, it doesn't mean that there's no hydrogen there. It just means that the star is so hot that the electrons are not in level 2 ready to absorb the light. So it's transparent. We don't see it. The light goes right through. Okay, so that's an O and a B. And now look what happens. So now let's get a little bit cooler. How about a type A? Here's a type A. Oh, look, for a type A, we can just about see that peak coming into the visible part of the spectrum. And look, here's H alpha, there's H beta. Look how deep those absorption lines, those are strong absorption lines of hydrogen. So we can start to see neat actual absorption lines. And there's lots of others. Here's an oxygen line from oxygen. Here's a line from neon. You can see some of these. Here's magnesium, although that's hard to see. Sodium is right in here. So you can see lots of different elements. We can start to see absorption lines from here's some calcium over here. So we can tell that all these elements are present in the star. Okay, so that's type A. Let's look at what's next. OBAF, type F. Before I show it to you, think about what you should expect. Type F is going to be a little cooler, so I should see that peak slide over to the right a little bit. Boom. Well, maybe not too much, but a little bit. So here's the peak coming over. But also look, these hydrogen lines are not as strong as the type A's, right? They're coming back a little bit. Let's look at type G. Oh, now we can really see it. In type G, look at that. The overall shape means that the star is getting cooler. That peak is coming back to the, that's between what, I'd say the peak is maybe 5,000, between 5,000 and 6,000. 500 to 600 nanometers. So definitely a cooler star. And look, now we're starting to see other elements. There's magnesium, a little bit of sodium is starting to come out. So it's true for hydrogen, and it's true for lots of different elements that different temperatures mean that they show up, whereas they don't show up in other temperatures. So knowing what elements show up at what temperatures, there's a table of this in the chapter, really helps to nail down the temperature and the type of star. Okay, so that's type G. Look at type K. Look at that. So now we have a peak that's going way over into the red and the infrared part of the spectrum. So this star is pretty cool. We don't see much in the way of hydrogen lines. Here's H alpha, H beta. We don't see much in the way of hydrogen lines. They're kind of mixing in with the noise. But look at the sodium. We have deep sodium and magnesium lines. Those start showing up in cooler stars. And then when we look at type M, the coolest star of all, look at that. The peak is way off into the infrared. We don't even see it. We're on the other side of the peak. And you can also see there's virtually no hydrogen lines. It should be right here, and it should be right in here somewhere. Instead, what we get are really broad features that start to come from molecules like titanium and iron. Here's argon, calcium. There's all sorts of different things that start popping up. But my point is that when you look at stellar spectra, you start to get a lot of information about the star. In particular, what's easy to tell, let me get back to this. Temperature is easy to determine. All we do to get the temperature of a star is just take its spectra and look and see where the peak is. I'm not going to ask you for precisely what kind of star something is. But all I'm saying is you should be able to tell the difference. If you look at just the shape of the spectrum, you should be able to tell, is it a cool star like a K or an M? Or is it a medium temperature star like a G or an F? Right, those have peaks in the medium to left-hand side of the graph, so somewhere in the blue to violet, or orange to violet, or yellow to violet. And then you could tell an O and a B star because you don't even see the peak at all. The peaks are way in the ultraviolet. So all I'm asking, we're not doing professional astronomy and trying to exactly type a star, but just by looking at the spectrum, you could have a pretty good idea if this star is basically hot, medium, or cold. So is it an O and a B, or is it more like a G, or is it more like a KM? So that's more or less kind of the thing once you look at a bunch of these that you'll get better at, which is the subject of the lab this week.